In this lesson, we show the principal thermodynamic cycles for both generating and operating machines, using different gas models, starting with the ideal gas and then moving to real gases and vapors, as well as reversible and irreversible examples. For each cycle, we calculate the main performance parameters and we learn to represent them using different thermodynamic diagrams. To make it more interesting, we are willing to use data of real cases. The lesson is split in more parts, also more videos. In the first part, we make a general introduction and we learn the Brayton cycle. In this lesson, we will see cycles that combine different cases: generating or operating machines, ideal gas, perfect gas, real gas, or vapors, reversible or irreversible transformations, and different diagrams: TS, PV, HS, or HP. And we consider both the thermodynamic and the technical work, with the solely constraints to have no gas mixture and no mass change. The task of every example is to find the energy exchanged in the process, both the work and the heat, and the cycle performance, eta for the generating machines, COP or EER for the operating ones. We remember that the definition of efficiency is only valid for the generation machines, where the thermodynamic work is given to the recipient, also for thermodynamic work positive. We start with the Brayton cycle. This cycle is used to describe the gas turbine trains, both the ones for aeronautical applications, for thrust generation, and for terrestrial application, power generation. Let's consider a cycle in the diagram TS. The first process, A, is the adiabatic compression. The second process is the isobaric heating. Then we have the adiabatic expansion and the isobaric cooling. All the steps are also represented in the schematic right bottom. We look for the heat and for the thermodynamic work of every transformation in order to calculate the efficiency eta. The first model we are using is ideal gas and isentropic transformations. We consider isentropic the transformations A and C. The second model considers still ideal gas but irreversible transformations, also not any longer isentropic. The third model considers a real gas and still irreversible transformations, to be closer to the real case. And then we perform a what-if analysis. As reference, we consider a real machine, the Solar Taurus 60. Power output is 5670 kW, the heat rate 11,430 kJ per kilowatt hour, and therefore we can express the efficiency, that is 31.4%. The exhaust flow is equivalent to 21.77 kg per second, and the pressure ratio 1 to 12.2. The exhaust temperature is 510 degrees. The performance are given under ISO conditions, that is entry air at 15 degrees and atmospheric outside pressure, let's say 100 kilopascal. And here we have the reference. In the first model we consider, as told, ideal gas and isentropic. We calculate the parameter R for pure air, the constant CV, Cp, and the mass is also given. We say 21.8 kg per second. The coefficient K, which is the ratio of the specific heats, turns into 1.4, and epsilon, which is K minus 1 over K, turns into 0.286. The pressure ratio beta is, as from the datasheet, 12.2, and this is dimensionless. The initial temperature under ISO condition corresponds to 288.15 Kelvin, the pressure 100 kPa, and the exhaust temperature, which is 510 degrees, corresponds to 783.15 Kelvin. We calculate T2 using the formula of the isentropic transformations. It is T1 into beta to the power epsilon and gives 315.9 Celsius. In the same way, we calculate T3 1327.2 Celsius. The chart in the diagram aside. What is the efficiency of this cycle? The efficiency, for definition, is the ratio between negative technical work and the sum of positive heat, where negative technical work equals the total heat, that is the sum of Q23 and Q41, because the other two transformations are adiabatic, and the sum of positive heat is just Q23. And Q23 equals the difference of the enthalpies of the points 3 and 2, that is the product of the mass, the specific heat at constant pressure, and the difference of the temperatures because of isobaric transformation. And that says 22,103 kilowatt. In the same way, we calculate Q of the transformation 41, that turns into negative 10,835 kilowatt. Negative technical work is also 11,268 kilowatt, and the calculated efficiency is 51%, that is not matching with the reality. Therefore, the first model is not correct. Let's see the second one. We keep the ideal gas, but we use irreversible transformations. We change only the two adiabatic transformations to irreversible. The transformation A from 1 to 2 moves from 1 to 2 prime, and the transformation C from 3 to 4 changes from 3 prime to 4. All the changes are represented in the charts aside. How to find those points? We have unfortunately no direct information from the gas turbine datasheet. Let's introduce the concept of adiabatic efficiency or isentropic efficiency. For a compressor, this efficiency is the ratio between the isentropic work and the real work. And because the transformation is adiabatic, the work we can express as differential enthalpy. Also, H2 minus H1, the isentropic work, over H2 prime minus H1, the real work. And for an ideal gas, since Cp is constant, we can express this efficiency by using the temperatures. For a turbine or an expander, the definition of adiabatic efficiency is the opposite, the ratio between the real work and the isentropic work. And also in this case we can use the enthalpies, and for ideal gas we replace the H with the temperatures, as for the expression 35. We assume for our case, being the efficiency of the compressor 78% and the efficiency of the turbine 83%. With these assumptions, we calculate the temperatures T2 and T3. T2 prime is T2 minus T1 over eta plus T1, where eta is the efficiency of the compressor, and we find 399.1 Celsius. For the turbine, the calculation is a little bit more difficult because we need first to calculate T4 prime. T4 prime from the equation of the isentropic transformation is T3 prime over beta to the power epsilon, and replacing T4 prime into the equation 35, solving for T3 prime, we find the expression 36 that says the temperature T3 prime is 1086.8 degrees. The heat over the transformation 2 prime 3 prime is H3 prime minus H2 prime and turns into 15,053 kilowatt. The negative technical work is the sum of the heats over the transformations 2 prime, 3 prime and 4 1 being the result 4,218 kilowatt. Finally, the calculated efficiency eta prime says in the new case 28%. The second model is actually better but still not correct. Let's see the third one, also real gas and irreversible. We keep the same temperatures found in the second model, but we calculate the remaining variables by using the application Thermonator. The found values of the enthalpies are displayed in green in the table right aside. Q2 prime 3 prime equals 17,120 kilowatt, something different from the result above. And Q41 turns into negative 11,258, also slightly different from the value found above. Negative technical work is 5,862 kilowatt, and the new efficiency eta second is 34.2%. Is this result good? Yes, if we consider the equipment in between. We have in addition a gearbox and a generator. The mechanical efficiency of a planetary gearbox we can estimate in 97%, and the electrical efficiency of a generator we can estimate in 98%. Therefore, the useful power P star is the product of the thermodynamic power PT and efficiencies over mentioned, also 5,572 kilowatt, as well as the useful efficiency eta star is the product of the thermodynamic efficiency and the above mechanical and electrical efficiencies. That says 32.5%. There is still a slight deviation versus the actual performance of the gas turbine Taurus 60 due to not perfect simulation of all the effects. We neglect the pressure loss over the transformation 2 prime 3 prime, as well as the change in the fluid chemical, because there is not only air but air plus combustion substances, and other effects are still not representable in a simple TS diagram. However, we can judge satisfactory our simulation. Now we want to run another simulation. What would happen if we increase the maximum temperature from T3 prime to T3 second 1300 degrees? The short way is to use the Carnot factor. Also, the efficiency of the Carnot cycle across the temperatures T1 and T3 prime is 1 minus the ratio of the corresponding temperatures. That says 0.788, and the corresponding Carnot factor is the ratio between the efficiency of the real cycle and the corresponding Carnot efficiency, and that turns into 0.434. Then the Carnot efficiency of the new cycle across the temperatures T1 and T3 second is 0.817, and assuming the Carnot factor is not changing, the efficiency of the new cycle across the temperatures T1 and T3 second is the product of the Carnot factor and the efficiency of the Carnot cycle, and that gives 35.4%. What would be the exact result? First, how the cycle will change? Answer: both T3' and T4 will change. We assume the adiabatic efficiency of the turbine does not change. It stays at 83%. From T4 we need to find then T4' using this equation. T3 second minus T4' equals eta into T3 second minus T4 second, where T4 second we have also represented in the chart is the ratio between T3 second and beta to the power epsilon, and that is 496.1 degrees, while the temperature T3 second minus T4' is also equal to the efficiency, that is 0.83, into the difference of the temperatures, 1300 minus 496.1 already found. And eventually we get for T4' the value 632.7 degrees. And the technical work is then from the Thermonator application negative 8511 kW, and the heat over the transformation 2', 3 second, 22,740 kW. With those values we can calculate the efficiency, that is 37.4%. Also in this case the Carnot factor cannot be applied very successfully. In the last part of the presentation we want to see together how to calculate the states of a transformation. To make it simple, we refer here to the ideal gas and isentropic model only, but the procedure can be used for any cycle. First, we need to define arbitrarily a reference state. We choose for the pressure 100 kPa, temperature 0 degrees, enthalpy 0 Joule per kilogram and entropy 1 kJ per kilogram per Kelvin. The volume can be calculated by using the state equation, as well as the internal energy by using its definition: enthalpy minus product between pressure and volume. For the state 1, we assume to know the pressure and the temperature, respectively 100 kPa and 15 degrees. As a consequence, we calculate the volume using the state equation, the entropy using its definition by means of the known quantities temperature and volume, and the reference entropy, as well as we can calculate the enthalpy by using its definition plus the reference value, and the internal energy as we have done for the reference state. In the same way, we calculate the thermodynamic variables of the state 2 and the thermodynamic variables for the state 3 and 4. The state 4 we will see in the next page. For the sake of clarity, we express the given parameters in red and the calculated ones in blue. We summarize also the result in the table, which is produced by the software Thermonator, and also we represent the chart of the transformation. Thank you for your attendance. See you for the next lesson. Bye bye.